To wrap up estimation series test, we have the alternating series estimation theorem that says that if we want to estimate a converging alternating series, if we want to estimate what the sum is, then what we're going to do is, first of all, justify that it meets the conditions of the alternating series. So is it a decreasing series, and does the limit go to 0? And if that is the case, then an estimation of using n, if we were to use n to make an estimation, then the remainder or the error, so meaning if we used n terms to estimate, so this is when S sub n, the partial sum, is used to estimate the actual sum S. Okay, so when we use S sub n, when we use n terms, 10 terms, say, if we use 10 terms to estimate the actual sum, then the remainder or the error, remember that R sub n represents the error in an estimation, then R sub n, which is just the difference between the actual sum and the estimation S sub n, the partial sum, will be less than or equal to the very next term in the series. So meaning if we were to actually use n terms, 10 terms, let's just say, if we added up 10 terms to estimate the actual sum of a converging series, then the error is going to be less than whatever the size of the 11th term is. So why does that work? Well, let's just look real quick. If we have an alternating series and it meets the condition, so remember for an alternating series, if we've used the alternating series test, that the two things happen. B sub k, first of all, B sub k is equal to the absolute value of A sub k. So it is a positive. B sub k is definitely positive. And the limit of B sub k is 0, and B sub k is decreasing. So B sub k plus 1 is always less than or equal to B sub k. It is decreasing. Okay, those two conditions, like that's just how we even use the alternating series test. We have to verify those conditions. So we're taking these little quantities, we're adding them up, the size of the quantity goes to 0, and every time we add a quantity, it is smaller in size than the previous quantity. So if you think about what that looks like, it looks just like this. We're adding up a bunch of stuff and we're zeroing in on a sum because we know that we're not going to even apply an estimation unless we know we have a sum, a convergence. And so therefore we're adding, so first you add B1 and you end up over here at some, partial sum S1. And then because it's an alternating series, then you subtract B2, but B2 is smaller than B1 and it's approaching 0. So then it goes, so then you go back to S2. Then you go forward to S3 by adding, by adding B3. But again, B3 has to be smaller than B2. So then you're ending up at S3. And then you subtract B4 because you add, subtract in an alternating series. And you end up over here at S4. And then you go forward to S5 by adding B5. Then you go backwards to S6 by subtracting B6. So these little B sub k's are getting smaller and smaller and smaller. We're alternating the sign. They're going to 0, and we're zeroing in on this S. So if I were to stop right here at S5, if I were to use S5 as the estimate, so if I were to use S5 as an estimate for S, then the error or the remainder another way to think of the error is the remainder left over, R sub 5 would have to be less than B6. Okay? It just has to be less than the size of B6. So whatever B6 is, so if I add up the first 5 terms, then I know my error is less than the 6th term. Okay, so that's what the alternating series test says, and just in general, I'll summarize it down here too. So just in general, we could say this. So we could say if A sub k converges by the alternating series test, and thus, and I'm not even going to put I'm not going to even put values on the index. You know, the index obviously goes to infinity, could start at anything. But if we were to say this, so then -1 to k, you know, obviously it looks something like this. It's an alternating series. Oops. Not to the k power, b sub k. And we decide to use S sub n to estimate it. So S sub n is then, of course, from k equals 1 to not infinity, of a sub k is used as an estimate for the actual sum then the error R sub n, which is just the difference, right? The error is always just what would be the difference in the actual value versus the value we used as an estimate, S minus S sub n, has to be less than or equal to the n plus 1 term in that series, then the very next term. So if we stopped at 10, then the error has to be less than the 11th term. Okay. That's what it's saying there. So I was going to write that out in words, but I think I'll skip that part and just do an example. So that's what it's saying. So let's jump into it. So how do we apply this? So here we've got a series. Let's find the sum of this series accurate to 3 decimal places. So a couple of things. First, you know, if you're asked to do that, the first thing you have to do is show that it actually does converge. So we would have to take this and we'd have to say, okay, well, that's very much an alternating series. So that's clearly alternating. It's got a switch on it. I think we can see pretty clearly. This will be a quick little proof. Okay, so this is definitely an alternating series. So if we take k equals 1 to infinity of -1 to the k plus 1 over k to the 4th, it's definitely alternating. My b sub k, which would just be the absolute value of -1 to the k plus 1 over k to the 4th, is 1 over k to the 4th. And check our two things here. Is this decreasing? And definitely it is decreasing. We can show that k plus 1 to the 4th has to be bigger than k to the 4th for k. This is true for k greater than or equal to 1. And so therefore 1 over k plus 1 to the 4th has to be less than 1 over k to the 4th for k greater than or equal to 1. So it's definitely a decreasing. The b sub k's are decreasing, and obviously, I'm going to circle these, the limit, we got to also show that the limit of b sub k equals 0 as k approaches infinity. And that is also true here. So I'm going to even just, I'll just write it one more time. Limit as k approaches infinity of 1 over k to the 4th definitely goes to 0. So we can check that box as well. Okay, so therefore, just a quick little reminder of how we show alternating series. Therefore, by the alternating series test, this series from -1 to the k plus 1 over k to the 4th from 1 to infinity converges. Okay. Now, that wasn't actually that wasn't all we were asked to show, but we have to show that first before we can use the remainder theorem. So we've got that. So we know that it converges. Now we actually want to find what that sum is accurate to 3 decimal places. So we have a couple of ways to go about this. We could first just generically figure out how many n's I need to do, and then add up that many n's. Or we could just start adding up. So sometimes with alternating series, the quickest way to do this, so we've got a couple of methods to find the estimate for the sum S. Okay. One of the ways we could do it is we know now that it's converging, so we know we have a sum from k equals 1 to infinity of -1 to the k plus 1 over k to the fourth. So we know it has a sum. So we could literally just start looking at the expansion of that sum. So if we plug in 1 here, we're going to have 1 minus, plug in 2. So I'm just plugging in the index here. So here's k equals 1, k equals 2, 3, 4, 5. So if I, then I'd have 1 over 16 plus 1 over 81 minus 1 over 256 plus 1 over 625 minus 1 over 1,296. Now, I could keep going, right? We're looking for the partial sum, but remember what our alternating series estimation theorem says is, it says if you add up n terms, then your error is going to be less than the very next term, the n plus 1 term. So check this out. If I add up these terms right here, so this is one way to figure out how many terms you have to add up. If I take S5, which would be the first 5 terms, look at what the 6th term is in absolute value. So in absolute value, this term, notice this b sub 6 right here, is actually less than 1 over 1,000, which we wanted to be accurate to 3 decimal places. That was our question up here. I know we kind of lost the question, but the question was figure out what the sum is accurate to 3 decimal places so that the error, that's another way of saying it. If we want to be accurate to 3 decimal places, another way to say accurate to 3 decimal places is your error is less than 0.001 or 1 over 1,000. So that's what we're actually looking for. And so it turns out on this particular case right here, we've ended up with a term where b sub 6 the 6th term, b sub 6, the absolute value of that, remember, I'm dropping the sign, b sub 6 is less than 0.001 or 1 over, if you take the absolute value, 1 over 1,296 is obviously less than 1 over 1,000. So that's as far as we need to go. So that's as far as needed for 3 decimals of accuracy. So that's as far as we need to go. So what we can say is here is like, well, oh, look at that. Like I added up, or I just started expanding the sum. I know this has a sum. I just started expanding it out, and it turns out that S sub 5, which is 1 minus 1 over 16 plus 1 over 81 minus 1 over 256 plus 1 over 625 gives me actually, let's see, I wrote this down, 0.947. If I plug that into the calculator, 0.9475539, which means that the actual sum of the series, right, from k equals 1 to infinity of -1 to the k plus 1 over k to the 4th can be approximated by 0.948 with error. We're within 0.001. We're within, by using that estimation, the first 5 terms, we have to be less than, we actually know we're less than 1 over 1,296, but that is definitely within 3 decimal places. So we can say that that is our error. So that is one way to do it, and sometimes that's the most effective way. If we're actually looking for a sum, just start adding up the terms until you get to a term that is less than the accuracy you want. Now, that term, you won't actually add that in. You don't need to add in the 6th term. You just add up the first 5 terms, and you know that your accuracy is within, is less than the actual next term, the 6th term. So if you add up 5 terms, you know your accuracy is going to be less than, your error is going to be less than the next term, the 6th term. That's one way to do it. The other way to do it is instead of starting with the addition, we could actually have started by saying, well, how many terms do I have to add up? Let's actually generically figure out how many terms do I have to add up, and then I can go back and add them up. So one way is what we just did here. So one method is just start adding. Okay. So just start adding up the terms. The other way is actually determine what n is. So here's another method. So another method would be to determine the value of n that gives us that accuracy. So determine the value of n needed. So let's take a look at what that would look like. So if that's what we were doing, if we want to know, we want S sub n, so again, we want S sub n, which is going to be equal to the sum from k equals 1 to n of negative 1 to the k plus 1 over k to the fourth. If we want that, but we want this time, let's pretend like we haven't done the previous part. So we want to know we want S sub n for this particular series where the actual remainder, which is the difference between the sum and what we're going to use, the partial sum, is less than 0.001, okay? Or 1 over 1,000. So if that's the case, if we want the remainder, well, we know that the remainder has to be less than or equal to the b sub n plus 1 term, and we want that to be less than 1.001, which is 1 over 1,000. So if that's the case, well, then we want 1, so we just look at what does that look like. Well, that would be 1 over n plus 1 to the fourth, and I want that to be less than 1 over 1,000. So I'll do my little cross multiplication. So 1,000 has to be less than n plus 1 to the fourth, or n plus 1 to the fourth has to be greater than 1,000. Take the fourth root. N plus 1 is greater than, the fourth root of 1,000 is approximately 5.62, so n has to be greater than 4.62. But again, we have to use whole numbers, so that means that n has to be greater than or equal to 5. So that means that we need S5 in order to guarantee, we need to add up the first 5 terms. So we need to go from k equals 1 to 5 in order to have this kind of accuracy. So we have to go from 1 to 5 of negative 1 to the k plus 1 over k to the fourth, and that means the first 5 terms. So that's telling me that I have to use the first 5 terms in the sum to be accurate to 0.001. Well, we already did this, so I'll just jump through this really quickly. So, of course, we did this in the first method. So this is 1 minus 1 over 16 plus 1 over 81 minus 1 over 256 plus 1 over 625. I don't have to go to the sixth term. That sixth term is actually giving me that amount, that desired accuracy. And so, therefore, this is approximately, what did we get? 0.948. And that is accurate to 3 decimal places. So you can pick your method when you're doing these. Sometimes I find that it is just faster if I'm going to be adding up the terms anyway. I just add until I get to my desired accuracy. So pick your method. You could determine the value of n needed and then add up those terms, add up the first 5 terms to get to that sum. Or you could just actually start finding the sum, adding up the terms, and when you get to the term that is smaller than your desired accuracy, you know you can stop one before that. Okay? All right, so that is our alternating series estimation theorem, and it is useful. If you've got an alternating series, you know that it's converging, then you can actually figure out how, it's our easiest estimation theorem, I should say. You can figure out your desired accuracy, or you can make estimations and know how accurate you are simply by looking at the term right past where you stopped your sum. So again, if you use the first 10 terms, then your accuracy would be within whatever that 11th term is. You know your error is going to be less than that 11th term. So as I said, it is our easiest of our estimation theorems to apply for the alternating series test.